Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. In this video, I'm going to talk about the nested interval theorem. So before that, let's recall some of the exercises which we have done before in the last video. Alright, so the first one which I did in the video was we took a collection of closed intervals Jn which were defined by a minus 1 by n comma b plus 1 by n for each natural number n, and we computed the intersection of all the jn's, okay, for each n, and we found that to be the closed interval ab. The second one I had left as an exercise for you all, a similar one in which jn was defined to be closed interval a comma b plus 1 by n. So this 1 by n was missing here for each n, and you all were supposed to compute the intersection of all the jn's. Those who have computed this should have obtained again the closed interval AB. Okay, so you can verify that. And one more was Jn, which was defined to be the closed interval minus 1 by n and 1 by n for each n, and then intersection of Jn turns out to be the singleton zero set. Now, what is the similarity between the intervals Jn that I'm taking in all these three exercises? So let's analyze that. So if you look at the first one, I have the number line here. And I have A somewhere and I have B somewhere here maybe. And then I look at J1. What is J1? J1 is nothing but A minus 1 comma B plus 1. So let me put that on the number line here. Right, so J1 will be somewhere here. So this I'll mark this is A minus 1 and B minus 1 would B plus 1 would be somewhere here. So this is my first interval. If you look at J2, that was A minus half comma B plus half. Again, I will put this on the number line and it will be somewhere in between here. So somewhere here. And here it was B plus 1 by 2. Okay, similarly, you can plot J3 and you can check it will still come closer towards A. Right, this is what we saw. So A minus 1 by 3 and B plus 1 by 3, and this keeps on moving. So one thing to note here is J1 is the biggest interval if you see. Inside that there is J2. Inside that there is J3. Inside that there will be J4, and this keeps on moving. Right? So what kind of closed intervals have I taken here? The length of the interval, if you see, it keeps on decreasing. Okay, so it's a decreasing, they are intervals of decreasing length. So I can say from here that J2 is contained inside J1, right? Similarly, J3 is contained inside J2, which is in turn contained inside J1. So similarly, how I can generalize this? N plus 1th interval Jn plus 1 is contained in Jn for each n, right? So the intervals, if you see in the first one, in the first example, it is of this type. I have a collection of intervals whose length is decreasing. Okay, by the length I mean if I have the interval a comma b closed interval, its length of this interval is this number b minus a. Okay, that's called the length of this interval. So if you see here, the length of the intervals, it keeps on shrinking. So each jn plus 1 is contained inside jn. All right, now if you see the second one, again same thing is going to happen. So J2 will be contained inside J1, J3 will be there in J2, J4 will be there in J3, and so on. So again, I have a pattern of this type. Jn plus 1 is contained in Jn. It's a subset of Jn. And even in the third one, if you see, the same thing is happening. Okay, so one thing to note here is whenever I take intersection of all these GNs in all the three cases, I'm getting non-empty sets. In the first one, we got closed interval AB. In the second one also we got closed interval AB. And in the third one, this turns out to be singleton set 0. So one thing to note here is that whenever I take a collection of closed intervals whose length is keeping on decreasing, it keeps on decreasing, and then when I take intersection of all such intervals, intersection of all GNs, that is always non-empty. This is the observation that we can come out by looking at these three exercises which are done in the last class. Fine. So the nested interval theorem is based on the idea which we saw in these three examples. So nested interval theorem says let Jn be the collection of closed intervals a and bn. So J1 will be closed interval a1 b1, J2 will be closed interval a2 b2, J3 will be closed interval a3 b3, and so on. All right. So I have taken a collection of closed interval Jn, and what kind of intervals? The intervals in R such that Jn plus 1 is contained inside J1. J1 plus Jn plus 1 is a subset of Jn. So again, I've taken a collection of intervals whose length is decreasing with n. All right. So this condition here, it only tells me that okay, J2 is contained inside J1. Again, J3 is there inside J2. J4 is there inside J3. Okay, and this keeps on moving, and this is what this condition tells me. And this is happening for each n in the set of natural numbers. Then, when I take intersection of all these GNs, this intersection will be a non-empty set. By a non-empty set, I mean it will be a set having at least one element in it. It could have more elements also, but to show that it is non-empty set, it is enough for us to find one element which is there in intersection of all these GNs. All right. So before formally proving this theorem, I will give you all a rough idea, how the proof is going to go about. Fine. So let's assume that the result is true. So we are taking a closed collection of closed intervals whose lengths are decreasing, such intervals Jn's, and supposing intersection is non-empty. Okay, so supposing I have found a point C inside intersection of all the Jn's. Let's assume. All right, so I'm just looking at the idea of the proof before formally starting with the proof. Now it is there in intersection of all the Jn's, meaning what? It is there in each and every Jn. So this implies C, this point is there in Jn for all the natural numbers n. So it is there in J1, it is there in J2, it is there in each Jn for every natural number n, right? But what is Jn? Jn is nothing but the closed interval a and bn. That means the point C is there in the intervals a and bn for all natural numbers n, right? And when do we say that a point C is coming in the closed interval? By the definition of the closed interval, this means an must be less than or equal to C, that is must be less than or equal to bn for each n, right? So now what I'll do is I will form one set capital A. All right, I'll form a set capital A which consists of all the first elements of the intervals Jn. That means A1, A2, A3, A4, A5, and so on. So all the An's I'll collect. So all Ai's, say I'm collecting, where I is a natural number. Right? So these are all the first points, the left hand points of the intervals Jn's. So all those points i's I've collected. You can also say this as an, where n is a natural number. Same thing it is. All right. So this I is just a notation. Now, if you see, the C is bigger than or equal to an for every n. That means C is bigger than or equal to a1, a2, a3, a4, a5, and so on. That means C is bigger than or equal to every element of the set capital A, because in capital A I have collected all these A's from here, right? So that means C is an upper bound of A, correct? C is an upper bound of A. Also, if you see, all Bn's are also bigger than or equal to An's. That means all the Bn's are also upper bounds of An's. So if I take BK's are also upper bounds of the set A. So I have C as an upper bound of the set A and Bn's all the BK's, where K is a natural number. Okay, just I've picked up the notation K here. So there are upper bounds BK's now, and C is also an upper bound of the set A. And there are lots of upper bounds, in fact, infinitely many upper bounds BK's, which are bigger than C. So that gives me a hint somewhere that the C must be a least upper bound of the set A. All right. This gives me a hint that the C which we have picked up here must be the least upper bound of this set A. And that is what we are going to prove. So we will catch hold of the C which is in least upper bound of the C. That is the supremum of the set A. And that supremum of the set A, we will show that it is coming in intersection of all the Jn's. And because of that, this intersection is a non-empty set. All right. And that is that C which we had started with here. We will show that that point is actually the supremum of the set A. That is the least upper bound of the set A. So this is the idea behind the proof of this theorem. All right. So let's prove the result formally now. This was just a rough idea, a rough sketch of the proof. Okay. So before starting with the proof, I will just jot down what is given to us about the J's, the hypothesis of the theorem. So it's given to us that Jn is of the form Jn is of the form closed interval a and bn for each n. This is one thing. And along with this, we know that Jn plus 1 is a subset of Jn, and this is true for all natural numbers n. Okay, so what this condition means is, if you pick a bigger natural number, let's say what this condition means is, if I pick a number alpha which is greater than beta, all right, if I pick up a natural number alpha which is greater than beta, then J alpha will be a subset of J beta. All right. So that's what that condition means. And what we need to prove that is a claim is intersection of all the J's when I look at this is a non-empty set. So we need to find a point in this set. All right. So before proving, let me put this on the number line. A1 is the biggest one, so A1 is here and B1 is here. E2 is the next one, so it is slightly smaller. So let me put it this way. Same way A3 I have here and B3 I have here. A4, B4, and this keeps on moving this way. Okay, it keeps on shrinking. And what I have to show is, I have to show that there is a point in intersection of all of them. So somewhere here, there is a point which is there in all the G's, right? So as discussed in the idea just now, we will form a set. So I will define a set A, And in this set, what I'll do is I'll take all the left endpoints of each and every interval. So I'm taking A1, A2, A3, A4, and so on, all the A's. So this is nothing but collection of all the A's such that n is a natural number. So I'm taking A1, A2, A3, all the left endpoints of each and every interval J, right? So from the diagram, if you see, uh, each B, if you see here, okay, each Bn, if you see here, that is bigger than or equal to each of the E's. That is one observation that we can make from here, right? So each Bk is bigger than or equal to each A's, okay, each An. And before that, note that A1 is coming inside A because it is the left endpoint of the interval J1. This means the set A is non-empty. Okay, so we are having a non-empty set, and this is actually a subset of R. Okay, because each A there, A1, A2, they are real numbers. So that is actually a subset of R, and it's a non-empty subset of R. Now, if you see each from the diagram, it's quite clear that each Bi, Bk is bigger than or equal to each An. So what we will do is we will show that An is less than or equal to Bk for all n and for all k. Okay, for all natural numbers n and k. So each An is less than or equal to each Bk. That means every B, if you pick up any B here, that will be bigger than or equal to every A from here. Alright. So that depends on k and n. Now I have two natural numbers with me. So we will look at different cases based on k and n. Now k and n are two natural numbers. So it is possible that k is less than or equal to n, right? If k is less than or equal to n, n is a bigger number. And here we saw that if alpha is bigger than beta, then j alpha must be a subset of j beta by the definition of the intervals, right? So from here, Jn must be a subset of Jk because k is less than or equal to n. This implies Jn is nothing but a and bn closed interval. That's a subset of Jk. That's akbk. So this is what I have if k is less than or equal to n, right? Now if you try to put this on the number line, this is actually coming from one of the exercises that I did in the last video. If a closed interval is a subset of one more closed interval, then we have the relation between their endpoints. So AK, BK is the bigger interval here, and inside that there is A and B. So it will be of somewhat like this. Okay, so therefore what I have is AK is less than or equal to AN, that is less than or equal to BN, and that is less than or equal to BK. So from here it's quite clear that AN is less than or equal to BK, right? Therefore AN is less than or equal to BK, and this will be valid for all k and for all n, which are natural numbers. So that's what I wanted to show, but we have shown it for the case when k is bigger than or equal, k is less than or equal to n, right? So the next case is if k is bigger than n, then what happens? So if k is strictly bigger than n, if k is strictly bigger than n, then k is a bigger number compared to the natural number n, right? That means in this case, jk is going to be a subset of jn because k is a bigger number, natural number compared to n. What will this imply? This will imply jk, which is akbk, is a subset of jn, which is an bn. Correct? That means this interval is a subset of this interval. So finally what I have is, if you plot this on the number line, how it will look. I have an bn, which is a bigger interval, and inside that I have akbk. Again, if you see, you will have that relation which I spoke about in the last video. So an will be less than or equal to ak, which will be less than or equal to bk, which will be less than or equal to bn. So again, I have an is less than or equal to bk for all n and k, from here and from here. An is less than or equal to ak, and ak is less than or equal to bn. So this is going to tell me that an is less than or equal to bk for all natural numbers k and a. So finally what we have proved is an is less than or equal to bk for all natural numbers k and n. So each b is bigger than or equal to each of those a's. Okay, so they are coming from the gn, the way gn is defined. I hope that's clear. So this also means that all the ans are less than or equal to b1 when k is equal to 1. So in particular, if I look at k equal to 1, if I pick up k equal to 1 here, what will I get? An is less than or equal to b1. K I have already fixed to be equal to 1, and this is valid for all natural numbers n now, right? So I need not specify belongs to n, because it's understood that this n is a natural number. That means this b1 now is bigger than or equal to all the ans, and ans are the elements of the set A. If you go back and see, that's how the set A was defined. A is a collection of all the ans. That means I have found a number b1 now which is bigger than or equal to each and every element of the set A. That means b1 is an upper bound of A. Right? Actually, each bk is bigger than or equal to an, but to say that A is bounded above one element, one real number b1 is enough for me. Okay, if you don't like this number 1, you can take k equal to 2, and you can say that b2 is bigger than or equal to all the ans, and hence the set A is bounded above. Right? So b1, we have found the upper bound for the set A, therefore A is bounded above in R, and A is also a non-empty set. So A is a non-empty set which is bounded above in R, right? And therefore by least upper bound property, for the set A, what we have, this set A is going to have a supremum. So there will be a real number C such that C will be the least upper bound of A. That is the supremum of A. Correct? So this is, again, we are using this LUB axiom here, which is one of the most important properties in this chapter. So we have found a real number C which is the least upper bound of the set A, right? As discussed earlier, what we will do is we will show that this C which we have obtained here, which is the supremum of A, is there in intersection of all the J's, right? So this is the idea that we had discussed earlier before beginning the proof. If you go back and check, you will find this. So we will show that C is there in intersection of all the J's. So that means I'll have to show that C is there in each J. Now C is the least upper bound of A. That means it is an upper bound of A. So first we can observe that An is less than or equal to C for every natural number n. This is because C is an upper bound of A, right? So it has to be bigger than or equal to each and every element of the set A. Also, if you go back now, we showed that each bk is bigger than or equal to each an. In that box, if you can see there, each bk is bigger than or equal to each an. That means each of those b's is also an upper bound of the set A, right? Also, I will use the notation Bn here. Bn Bn's are upper bounds of A because they are bigger than or equal to all the n's, so they are upper bounds of the set A. But C is the least upper bound, right? And C is the least upper bound of A. So C being the least and all the Bn's being other upper bounds, C must be less than or equal to Bn's because C is the least upper bound. So this is again valid for all natural numbers n. So if I pick up this inequality and I club it with this one, what do I have finally? That means An is less than or equal to C and C is less than or equal to Bn, and this is valid for every natural number n, right? So this implies the number C is there in the closed interval A and Bn by the definition of the closed interval A and Bn for each n. But what is the closed interval A and Bn? That is nothing but a Jn's, right? So that means C is there in each of the Jn's. This is nothing but Jn, and this is true for all natural numbers n. That means C is there in each and every Jn, and therefore this point C is there in intersection of all the Jn's where n is running over natural numbers. So what we did, we found a point C in the intersection, and hence intersection of all the Jn's where n is a natural number is a non-empty set. And this is what we had to establish. Alright. So this is the proof of the nested interval theorem. Alright. So if there are any questions regarding the proof, you can put it in the comment box and I'll try to answer them. Alright. And these are my references. Thank you.